Hello and welcome to Nature Live Online, the show where we bring the Natural History Museum in London straight to your homes. Now, from the dinosaurs in our galleries to the giant squid in our basement, join us for a chat with museum scientists and from all around the world. Now, today we're looking at awkward relatives in nature. Animals that look very different but are closely related, or animals that look a lot like each other, but they couldn't be further apart. Stay with us to definitely be surprised. And as always, as we chat, if you have any comments, any questions, send them through and we try to get through as many as possible. We would love to hear from you. Now, to talk about these awkward relatives, we have Dr. Natalie Cooper with us. She is a senior researcher of vertebrates at the museum in London, and it's an absolute pleasure to have Natalie with us today. Hello, Natalie.
Hi, afternoon.
Welcome to the show, Natalie. Welcome welcome to the show and thanks for joining us. Now, Natalie, in case you didn't know, and also for all our viewers, this show is part of the Operation Earth program, which is a national program in collaboration with the Association for Science and Discovery Centres and the Natural Environment Research Council. And this program will engage, inspire, and involve families with school-age children with amazing stories and science of the environment, and will explore world-leading environmental research and show us how it is relevant to everyday life. Now, there's loads of stuff happening as well at the Natural History Museum in London live. There are activities happening there and events happening there. So if you happen to be in London, pop along and have a look at what our colleagues are doing over there. But going back to Natalie, I was really surprised when you told me that the thing that we had in the front page of the show, even though it looks a lot like a hedgehog, is actually not a hedgehog. It's actually something called a tenrex. And not only is not a hedgehog, it's actually absolutely not related to hedgehog, apart from being a mammal. Is that right?
Yeah, that's completely right. So on the right-hand side here, we've got our lovely hedgehogs that we get in the UK. And on the left-hand side is a tenrex, a hedgehog tenrex specifically. And you can see they look really similar. They've got the cute little pointy nose and they've got the spikes, but they're really distantly related. And just how distantly related, I'll show you in just a moment.
We're going to be talking about that. But although sometimes we can be tricked into thinking the two organisms are related, just like the hedgehog and the tenrex, when they're not. Normally, animals that are related to each other, they look very similar, right? So, for example, if we look at hummingbirds and all the different species of hummingbird, they all look very similar. Is that right, Natalie?
Yeah, so generally we can use what an animal looks like to give us an idea about which group it belongs to, or what its relatives might be. And you might see this in things like bird books. So hummingbirds are a good example. They've got this kind of hummingbirdy kind of blueprint. So they all are quite small. They've all got these long pointy beaks, and they might vary in how long or how curved those beaks are. But in general, they all look kind of like a hummingbird, and that's because they're closely related.
And why would we expect two animals that are closely related to look like each other? Because that's what we will feel like. We see two things that look similar and we go, okay, there must be a similar thing. Why does that happen?
So it's because so things that are closely related evolve from the same ancestor. So they evolve from common ancestors. We normally can think about this using phylogenies. So here's a phylogeny, or what we call a family tree, on the screen here, and I made up one basically. So at the tips of the tree, we've got these little shadows, these silhouettes, and these are different animals. So we've got a fox, a dog, a horse, and a fish. And the branches of the phylogeny, or the family tree, join them up depending on how related they are. And so you can see foxes and dogs are the most closely related, and then they're closely related to horses, and then horses, dogs, and foxes are then also related to fishes. We can also look at the time involved. So the branch lengths give us an idea of how long the time has been to get to that point. So short branches is short amounts of time, long branches is long amounts of time. So what we're really interested in is how long ago did these species we're interested in share a common ancestor? And so the most recent shared common ancestor of these is often what we're interested in. So if we have a look at the next slide, we can see that this is the most recent common ancestor of foxes, dogs, and horses, is where that yellow star is. And so at some point in the past, they all shared an ancestor, and then they've evolved from that ancestor to look like they do today. So if your most recent common ancestor is pretty recent, then you're likely to look fairly similar. We expect that you're going to look fairly similar because you've evolved from something that looked pretty similar and you've not had long to do so. Whereas if your most recent common ancestor is a long, long time ago, then you might look more different. And we can read those times off by using these branches, as we've shown here, that give you this idea of how long ago things happened.
So if we go back to hedgehogs and tenrecs, what about them? Why? What's going on in their phylogeny, in the group trees, where they belong?
Yeah, so if we look at a phylogeny of all mammals, and so we've got a phylogeny here, and at the tips, these little icons are showing you big groups of animals. So if we just circle the one with the monkey on it, so this is not just one species of monkey, this is all monkeys, apes, humans. So some of these tips will have thousands of species represented. So if we work out where hedgehogs and tenrecs are in this tree, we can actually draw a little circle around them, and you can see they're quite well separated. What's really important when you're reading a phylogeny is we're not really interested in how close together they are vertically. What we want to do is work our way backwards through the tree, along the branches, to find the most recent point where those two things shared an ancestor. And for tenrecs and hedgehogs, you can see we've used these dotted yellow lines, and it goes all the way back to the beginning of this tree. So this is the beginning of the placental mammals, so about 160 million years ago. So hedgehogs and tenrecs have not had a common ancestor for over 160 million years, and yet they still look really similar. And we call this convergent evolution. So we think what's going on is that they have really similar habits, they have really similar diets, and so they've evolved similar solutions to the same problem. And that's what we call convergent evolution.
That's amazing. So that's the reason why that happened. There were two things that so far apart, they look so similar. And does it happen a lot in nature? Are there other examples in nature of this kind of thing, or only tenrecs and hedgehogs?
Oh, there's loads of brilliant examples. So we've got, so dolphins are a really nice one. So dolphins and things like ichthyosaurs. So dolphins are mammals. Ichthyosaurs are extinct reptiles, but they both have a really similar body shape because, again, they're adapting to similar conditions. So trying to move through water, and they've come up with a similar solution to that problem. So making this nice streamlined shape. Another good example would be things like bats and flying squirrels. So they're not quite as distantly related as dolphins and ichthyosaurs, but they are not, they're not in the same group. But again, they've done the same kind of idea, trying to move between trees or trying to move through the air. And so they've got these big flaps of skin in order to help them do that.
Mm-hmm. So it's really, really amazing. It's just a solution to a problem that happens, and why not using the same strategy, I suppose. So that's why they end up looking so similar. Now, Natalie, we're going to keep talking about these awkward relatives in a minute, but I just wanted to remind everyone that if you have any questions, you can put them on the chat, and we'll ask Natalie. We'll get through as many as possible. But also, if you're enjoying the show and you want to support the museum, you can also make a donation. So you can click on the donation button on the YouTube chart. I think it's just above it, or you can go directly to our website and donate from there. So we'll put a link on the chat, and any donation is always helpful. But stay with us if you're enjoying the show, because there's so much more to come. But remember to send your questions as well. Now, Natalie, let's go back to our tenrec. We've established now it's not related to hedgehogs, even though they look uncannily like them. But actually, if we actually look at the animals that they are related to, all the tenrecs, in fact, there's also a bit of a surprise there. So let's have a look at all the tenrecs in their own same group, because maybe they don't look that much like hedgehogs, we would imagine. So let's see if we have a picture of the other tenrecs that share that commonality with them. Okay, there they are.
They're great. So anyone who knows me knows I'm obsessed with tenrecs. They're my favorite group of mammals. So this is just one family of mammals. So they're all really closely related. They only live on Madagascar. And there's about 35 to 38 species. We're often finding new species when we go out and do field work. But given how closely related they are, they really don't look like each other at all. So we've got our hedgehog tenrecs that we've already talked about. We've also got tenrecs that look a bit like shrews. And we think that some of these may even be able to echolocate, a bit like bats do. There are also tenrecs that look a little bit like moles, and they've got the same kind of modified front forelimbs that moles do for helping them to dig. So same idea here. They're similar adaptations to similar problems, so living underground, but completely different parts of the mammal phylogenetic tree. My two favorite ones, though, so up in the top left-hand corner here, we've got the lowland streaked tenrec. And so these in the wild, they really are bright yellow and black stripes. So like a bee or a wasp, really spiky. But one of the coolest things about them is that they have modified spikes on their back that they sort of rub together. They call it stridulation. So it's kind of similar to the way that grasshoppers produce sounds by sort of rubbing their legs. So they rub their spines together to make these really high-pitched sounds that we can't hear, but their babies can. So their babies will follow the mummy around, trying to get through these the undergrowth, sort of following along, hearing these sounds. And then my other favorite one, so up in the top right-hand corner here, this is a baby one, but there are the bigger ones, so the adults are actually about the size of a medium-sized dog. So there's a huge amount of size difference in this group as well. So you've got these ones that are about this big, medium dog size, small to medium maybe, but you've also got ones which are really teeny. I always think of them, they're about the size of a What's-It. So you've got this huge range of sizes, but the big ones hold a couple of records in mammals. So they have the biggest litter size of any mammal, so the most number of babies in one go. So they can have up to 32 babies at once, that's a lot of babies. And then to match that, my absolute favorite fact to tell people is they have the most nipples of any mammal. So they've got between 32 and 34 nipples. So yeah, a lot of nipples. So you've always got to bring that in when you're talking about tenrecs.
That's amazing. I can tell why you love them so much, Natalie. You've seen them in the wild as well, and you work with them. So we've got a couple of pictures of you with these different tenrecs as well. And you've got an amazing story as well about when you were studying them. Now, we've got loads of questions as well coming in, Natalie, so I'll be asking you some of those questions in a minute. But can you tell us what's going on in the next picture that we're going to see? Because I can't see any tenrecs, but there are definitely a few there.
Yeah, so somebody's asked in the questions, when we're talking about tenrecs, so it's TENREC, so tenrec. If you want to look them up online, which I recommend you do, they're very cool. So this picture is quite a funny one from fieldwork. So when we catch the smallest of these tenrecs, they're very similar to shrews. So you might know that shrews have a very high metabolism. They need to keep moving and eating in order to keep going. Or if they get a bit too cold or they stop eating, they will die. And so when we catch them overnight in a bucket trap usually. And then we have to collect them to do anything with them. And so to keep them safe, we pop them into a bag, which you can see I'm holding, and gently tie that up so that they don't hurt themselves by falling off my hand or something. But then to keep them warm, you have to stuff them up your jumper. So in this particular picture, I think I've got maybe 5 bags with different tenrecs up my jumper, close to my skin, to keep them warm. And they sort of revive pretty quickly, and you end up with lots of little tenrecs kind of scrabbling around. So that's what we were always referring to as my tenrec pregnancy, because I had an awful lot of tenrecs up my jumper in that fieldwork trip.
So I think that we can say that definitely your awkward relatives as well, if you had your tenrec pregnancy. Now, Natalie, let's keep talking about these amazing animals and their relatives. But we had some interesting questions coming through. One question I think is quite interesting. How and why did the common ancestor evolve into other organisms? So yeah, the common ancestor is always something that we talk about. It's kind of like a vague image of something that is nothing that we know now. But how did it evolve into these other organisms? Have you got a short answer for that?
So probably natural selection is the nice short answer. And so it takes a really, really, really long time. But we think that the main way that evolution happens is you have a population of animals, and then one of them changes something slightly, which makes them actually better at living in their environment. So maybe if it's a dolphin example, maybe they become slightly more streamlined or slightly better at catching fish. And then that means they're more likely to survive. They're more likely to pass their genes into the next generation. And then their babies are also likely to have that adaptation, which helps them. And so over time, you see these small changes gradually building up until you get these big changes that create new species. We might also see things like where things are on different places. So if you're on an island and the island splits due to tectonics or something, you may end up with different species evolving on different islands. So there's a lot of stuff going on, lots of really fine scale, small changes that build up over time, and then these big dramatic events which could end up with this happening. But like Cristina says, normally we don't know what that common ancestor would be. There are a few examples where we can have a pretty good guess, but for the most part, a lot of the diversity that used to exist, we don't know anything about because we don't have a brilliant fossil record. Yes, there's another thing we were going to talk about is how these animals, these tenrecs, are actually related to other groups. So within tenrecs, obviously they look really, really different to one another. But sort of if we go out a little bit further in the phylogeny, they actually are part of this group called the Afrotheria. So this is a big old group. So if we go back to that previous slide, they're a big and old group, the Afrotheria. But the really cool thing is that tenrecs, the hedgehoggy tenrecs and the shrew tenrecs, they're actually more closely related to all of the animals in this picture than they are to any of the things that they look like. So each tenrec is more closely related to an elephant, for example, than it would be to a shrew or a mole or a hedgehog, which is what it actually looks like. So the Afrotheria are this incredibly cool group with all these different things. So there's an aardvark in there, there's hyraxes, elephants, golden moles, there's an elephant shrew, and then there's also the sirenids, so the dugongs and manatees. So these are more closely related to tenrecs than things like hedgehogs, which I think is amazing. Khalil.
That kind of convergent evolution is fascinating. And some of our eagle-eyed listeners might notice that I'm not Cristina. Having some technical issues, I am here to take the rest of the show. This convergent evolution, I think, is a really, really important concept it's shaped quite a lot of evolution in large groups of mammals. Although I think Cristina is back soon. So let's lead into that by asking, how can such distantly kind of situated and kind of distant groups be so similar in function and form, but also how can such closely related organisms like the Afrotheria be so different in form?
So I think that's a really good question. And again, I think this comes back to natural selection. So we've got animals that have got similar problems, dealing with them in similar ways. But at the same time, within something like the tenrecs, there's lots of different niches that they occupy. So they all do slightly different things. So again, they've evolved to fit their environments or fit their diets. So they have this kind of evolution instead. And another example, which is the slides that we're currently showing you, is a really cool one, is you can see in parrots and falcons and eagles. So you might imagine that falcons and eagles are really, really closely related because they look really similar. They've got the hooked beak and the nice talons that are going out and catching their prey. And parrots, well, everybody knows parrots, right? They don't seem very similar to either of those groups. But if we look at the bird phylogeny, which is what's on the screen at the moment, so the family tree of birds, the yellow here is showing you, if you work your way back through the tree and see where parrots and falcons sort of join up, that's the yellow star. So parrots and falcons are really, really closely related, despite not looking very similar at all. At the other end of things, if you were to join up the falcon to the eagle, you can see that's this red line that goes to the red star, which is a lot further back in the tree. So there's a lot bigger difference in when these things evolved. So yeah, again, another weird example of awkward relatives where parrots and falcons are more closely related than falcons are to eagles, which we wouldn't expect just by looking at them.
And fascinating as this is, why does it matter? Why is it important that we understand these evolutionary relationships between different groups of animals or organisms in general?
Yeah, so that's a really good question. And so there's lots of things to think about here, but I obviously think all of this stuff is really cool. And I have some Natural Environmental Research Council research, which is looking at this in bird beaks. So thank you, NERC, for sponsoring today's show. But equally, there's an important thing about conservation. So we're often talking about biodiversity. We need to conserve biodiversity. And, there's never been a more important time for us to be really carefully thinking about how we protect the environment. But we also don't have that much money. So we're trying to make sure that we don't have a huge amount of money, and we do have to try and make priorities. So how do we prioritize different areas or groups to be preserved? So if we've got one area that's got 100 species and one that's got 50, our natural inclination might be, well, we'll save the 100 species area. And that's fine. We're saving more species that way. But if in those 50 species, we've got species that are really different and really diverse in the same way that the Tenrex are, then these species are probably really important for keeping the ecosystem running. And when it's things like plants, it might be giving us as humans different services. So there may be some plants which are really good at soaking up CO2, some that are great at preventing flooding, or great in drought conditions. And so we might also want to think about preserving that kind of diversity as well, rather than just numbers of species. So I think thinking about morphological, so sort of shape and size and form diversity, but also the functions of the species within the ecosystems is going to be really, really important when we're moving forward and trying to make these really hard decisions when we're trying to do conservation planning.
I think that's a really interesting point you make about diversity and biodiversity. It not just being one measure. There are lots of different ways you can measure it and lots of different ways you can approach it. And it's important that we try and combine as many of those as possible to get the best picture of what's actually out there and what we're living with, what we're losing, and what we can save.
Exactly.
So we're reaching the end of our time, but I think we've got time for a couple more questions from our audience. There was one question from Sophie on YouTube, which is going back to those tenrecs we were talking about. And it's a specific question. So if we're comparing tenrecs and their kind of European, not going to say relatives, but equivalents, is, for example, a baby hedgehog tenrec born more or less kind of developed than a baby hedgehog?
Pretty similar, actually. So yeah, baby hedgehog tenrecs are pretty capable of getting up and immediately running around after their mum, usually. So yeah, I don't think there's no big difference there. So they're not, I think maybe what Sophie's thinking about is marsupials, which are even, so the split between marsupials and things like hedgehogs and placental mammals is even further back in evolutionary time. And in marsupials, of course, you get those really weird sort of the baby kangaroos, which are like little jelly beans. And then they're really poorly developed and they develop in a pouch. Whereas hedgehog tenrecs, they are placental mammals. They still develop pretty similarly. There's just, I don't know how they do it. I don't know how they manage to have so many babies, but yeah, they're a very weird species that we should try and find out more about.
And our next question kind of speaks to, on the subject of what we were talking about earlier about the different ways of looking at diversity and species numbers and things like that. I guess that those relationships also get a bit complicated by the language we use to talk about them. So, for example, giant pandas, red pandas, they look very, very different. How closely related are they?
Yep, so they're really closely related, I think. So they're not bears, but they are in the same, they're in carnivores. So they're definitely way more closely related than this big split among tenrecs. But yeah, I mean, words and language is going to be a really interesting way of thinking about things. And actually, I think it's there's an additional side to this, which is how do humans see stuff? So one of the problems when you're looking at hedgehog tenrecs and hedgehogs is now I look at them and I think, well, they're really different. Why would we think they look similar? But if you see them for the first time, you think, oh, they look pretty similar. And that's because humans have this habit, it's called Paradoia, where you find pictures in things. So if you've ever seen that thing where you look at a box and it looks like it's got a smiley face on it, that's humans trying desperately to find pattern in chaos. And so a lot of these examples of convergent evolution are likely, at least in part, due to the way that we as humans process what things look like. So if we look more closely, sometimes we find they're maybe not as similar as we thought they were.
And that kind of pattern recognition has stood us in really good stead evolutionarily over the years, but it does sometimes complicate things a little bit. On the subject of bears, we've got a question from Timothy, who's asking, do bears have any of these so-called awkward relatives?
Ooh, that's a good question. I mean, I would say that within bears, pandas are pretty awkward, right? Pandas are doing something incredibly different. And if you look at the morphology of pandas, there's some very weird things going on there. So I don't think you
How weird are they?
Oh, there's, they've got that funny thumb thing, which is not actually a thumb that they use for stripping the bamboo. They've got funny teeth, and they're also a lot smaller than other bears. So I think if you just saw a panda without knowing what it was, you probably wouldn't necessarily go, oh yeah, that fits within bears. I mean, there are only 8 species of bear, and the fact that pandas are in there and grizzlies, they do look quite different to one another.
Yeah, I mean, I guess again, that speaks to the language we use around stuff, and how we can classify species. Is it morphological? Is it genetic? Is it in terms of their function and what they do? And yeah, I think the more we can combine those approaches, we can have a better, more complete picture of what we've got. So I think that brings us to the end of our time for today. Thank you so much, Natalie, for joining us. This has been absolutely fascinating, and I'm glad I managed to have this at the end of this conversation with you. Thank you. And thank you at home for joining. For another Nature Live online from the Naturalist Museum. Thank you and goodbye.